Jitter is one of the new analysis capabilities in the MSO8000 series oscilloscope. Using its deep memory and high sample rate, the MSO8 enables advanced characterization of these signal timing issues. Clock precision is critical for high-performance serial data transmissions. Let's look at how the MSO8000's jitter analysis package improves debugging and analysis of subtle timing issues. Jitter analysis is the characterization of the clock timing. Here we are looking at 35,000 clock transitions on channel 1 from a serial data transmission. TIE, or the time interval error, is one of the most useful methods for visualizing subtle changes in the clock frequency. The purple math trace is the TIE trend. This shows the sum of the errors in the period from the expected clock. Since the errors increase and then decrease linearly, we can tell that the actual clock period is fluctuating between a value slightly longer and slightly shorter than the expected period. We can use this information to look for periodicity in the clock fluctuations. We can use that measurement on the screen in the bottom left, or we can stop this signal and look at the cursors as well. We can move this cursor to the valley and look and note that the signal has a 10 kilohertz frequency. So the underlying clock is moving at a 10 kilohertz period between really two different values. From the histogram below, we can see that this is pretty evenly distributed and consistent. The instrument also shows the long-term statistics for TIE, cycle to cycle, and the positive and negative pulse width measurements at the top. These are the most common ways to characterize clock timing. The trend, period, and distribution are excellent visual debug tools designed to help engineers quickly find the root cause of their jitter issues. One of the advanced capabilities critical to jitter analysis is clock recovery. Depending on the signal type, some receivers will read the clock differently. The MSO8000 can use a constant, explicit, or PLL-based clock recovery. If we switch this clock recovery to a PLL-based mode, we can see that gets rid of much of the low-frequency fluctuations from the measurements for this clock. These analysis tools enabled us to determine root cause and ultimately reduce the clock jitter. Zoomed in on our final result, the MSO8000 can characterize picosecond level changes in the clock period. This is well beyond what can be visualized with a standard oscilloscope without deep memory jitter analysis capabilities. One of the new analysis capabilities of the MSO8000 series oscilloscope is the eye test or eye diagram application. We can use the eye diagram to measure complete signal quality, including looking at issues related to noise, timing, and bandwidth. Let's take a look at what an eye diagram is and how it helps us simplify debugging for complex signals, including serial data transmissions. Here we see our eye diagram test running on the MSO8000. We call this an eye diagram because of this shape here. What we want, ideally, for this data transmission is a nice open eye with an open space vertically and horizontally, allowing us to get very low error rate in our data transmission. This eye diagram is built with the high sample rate of 10 gigasamples per second and 10 million points. All those points are then correlated to the clock transition and then folded over on top of each other into a density display like this. That allows us to see how every transition looks compared to its clock point and the point at which we're actually calculating the data bit. We can actually see in this eye diagram there are a couple different issues impacting our results. One, we see vertically a lot of space here. This implies a certain amount of noise coming through the signal that might be affecting our ability to get a clear bit test at this point. Additionally, this rise and fall time on these transitions are pretty diagonal at about 45 degrees. In these settings, we'd like it to be steeper, giving us clearer corners in this eye diagram. That's likely a bandwidth issue, not allowing the signal to change fast enough. And we have a certain amount of frequency noise causing this to move back and forth, left to right, and causing this distribution here. So we're using the histogram to look at the crossing pattern and show us the distribution of those transitions. Now that we've identified the issues in this eye diagram, we went ahead and started to debug the problem. The first problem we found was the signal that was causing the amplitude noise. So we've been able to remove that, isolate that crosstalk, get rid of it, and reduce our noise on all of these signals. So now we can see how these signals are separated, the top layers, and we're starting to open the eye a little bit. Now we can clearly see that there's a bandwidth issue, keeping these signals from rising all the way to the top and falling all the way to the bottom transition levels. We still see a little bit of frequency noise, but clearing up the amplitude noise has helped us a lot. Now let's see if we can solve that bandwidth problem. After making some changes to our transmitter design as well as our cabling, we've been able to considerably increase that bandwidth. We now see with the same settings, the slope is much faster on both the rising and falling edges, giving us a much more open eye area. Combination of removing the noise, improving the bandwidth, has also really limited the total frequency and jitter noise as well. Now we have a nice open eye that allows us to go ahead and push our throughput by increasing our data rate if we need to really maximize the effectiveness of this serial data transmission. So those are the ways that eye diagram testing and a histogram can really help you to complete your signal analysis and signal fidelity measurements by looking at noise, bandwidth, and timing across a complete deep memory cut of measurements and serial data. By overlaying that data from the deep memory into a density plot for easy visualization, the MSO8000 makes eye diagram testing easy. Bandwidth is an important specification for any oscilloscope, but it's often hard to visualize how that might impact the measurements you make every day. Many engineers utilize a scope without sufficient bandwidth for the task, but adjust the amplitude on the display to see the signals that are attenuated. This isn't the whole story, especially when conducting signal quality measurements on critical embedded signals. The real-time eye diagram test is the best tool for complete signal quality. Let's look at how bandwidth affects the results of your eye diagram. One of the critical elements of the eye is the slope of the transitions. This is the rise time of the signal. Here we're looking at a high-speed clock in eye test mode. This signal shows 130 picosecond rise time, demonstrating scope bandwidth in excess of 2 GHz. With the MSO8000, not only can you use the eye diagram to analyze the signal quality of high-speed serial data, but the extended bandwidth, up to 2 GHz, significantly improves the accuracy of the rise time measurements over competitive products with less bandwidth. In fact, to ensure that the rise time error is less than 2%, the scope should have 5 times the bandwidth of the signal. With up to 2 GHz of bandwidth and eye diagram testing for complete signal quality analysis, the MSO8000 provides uncompromised performance at an unprecedented value.